Where'd you get that cool hat, John?
Well, I'm going to talk about that briefly.
Are we going to have it as a class hat?
Not really. I had to go. This cost a lot of money.
I was gonna say it wasn't free.
It cost a lot.
Okay, it's John's turn to.
Okay, thank you. My name is John McBride. For those who don't know me, so just call me John. You call me doctor. It makes me feel like I'm sort of responsible for your medical well-being or something, which I do not want to be. And if you say Brother McBride, then I think I'm going to be called to something, right? So just John is fine. I thought I'd bring in a few props. I'm wearing one of them. This is the Air Zermatt hat. This is the name of the helicopter company that we use to get back and forth between the village of Zermatt and the glacier. Although the best way is to walk out there. I've done both. The other prop is an ice axe, which I haven't used a lot, so I have a lot of its shiny patina on it, but I have used it to keep from sliding into a crevasse. So me and this axe have a special relationship. I'm here today because of this axe, so because I'm fairly clumsy without it. Okay, so I may hold on to it in a way that's maybe unnatural, but you'll have to get over it. It's also a good pointer as well. So what I want to talk about is a radar study that we've done, ground penetrating radar, or in other words, ice penetrating radar. This is a picture that I took of obviously the Matterhorn. And this is a study that got started several years ago with Summer Roper, who used to work here, now University of Utah, the other place. Other faculty that worked on this project, Scott Ritter and Dave Tinney, and a whole bunch of students. Okay, so this has been an ongoing project since something like 2009, I think, and it got started as actually a mega field trip. The idea for it began as a mega field trip. So who knows what type of project may come out of this trip that we're going to that we're planning now for June. Okay. So what I'd like to talk about is this actual science problem. It's not just a travel log here. What we're trying to do is to determine the distribution of water. And water, of course, whether it's liquid or ice, is related to temperature within alpine valley glaciers, those narrow kind of glaciers that you see in a lot of guidebooks or textbooks about the Swiss Alps or other places like it. And also the role of glacial ogives. Now, ogives is something you might not know what that means, but I'll explain that in a little bit. Basically, the wave patterns that you see as topography on the top of the ice. Is there some relationship between the water that's within the glacier, and therefore the temperature, and these glacial ogives? Now, I usually don't think of water being within a glacier. When I first started to study glaciers under the direction of Summer Roper several years ago, I had this idea, well, glacier is just ice. What else is there to talk about? It's just ice. Well, it turns out that's kind of naive point of view. Glacial ice can have a very complex temperature structure. And the way you get at that temperature structure is trying to figure out, well, where do you have ice versus water? And radar frequencies or microwave frequencies are an excellent way to do this, because microwave energy will respond quite differently depending on whether you have water in a solid state or in a liquid state. If you don't believe me, you can perform a little experiment with your microwave oven, if you have one at home. If you put ice in your microwave that's just really frozen right out of the freezer, and turn on your microwave, it'll just sit there for a while, it won't do anything. But you just put a tiny bit of water and it'll very quickly melt, because the properties of energy transmission is quite different in liquid ice, in liquid water versus solid water. So we use that property to use an ordinary ground penetrating radar antenna to actually sense temperature within the ice itself. So that means that we're actually just using the scattering properties of water versus ice as seen by the radar to intuit temperature. So that's kind of our objective. The reason we're doing this, the why, is that if we can understand the distribution of water within glacial ice, then maybe we can start to understand a little bit about why glaciers move back and forth. Of course, in this day and age, we're very interested in why glaciers retreat. So that's the ultimate why that we're trying to do with this study, which is ongoing. So, glacial ogives. This is a very nice picture showing a classic view of these wave patterns that you can see. Sometimes they're represented as topographic ups and downs. Sometimes they're just banded because debris will collect selectively within the troughs of the ogives and not on the crest. But that's a typical pattern you see. This is one from the Juneau ice field in Alaska. So basically, glacial ogives are transverse features. In other words, they are perpendicular more or less to the direction of flow. So they're transverse features that form at the ice falls of some glaciers, some alpine glaciers that are fairly narrow. If they're narrow enough, and if their speed is just right, then these features will form in the ice fall zone, which is not shown in this picture. So they're basically seasonal features, not exactly like growth rings within a tree, but somehow vaguely analogous to that. They're yearly features. So what is an ogive? It's a term borrowed from engineering and architecture. Just a picture from Wikipedia. Basically, it refers to a pointed arch. A pointed arch is called an ogival feature. And so we transferred that name to the glaciers themselves. Just another picture. This is from Europe, from Mont Blanc. Same type of feature that you can see on this glacier as well. So this is our study area. We're flying into Milan. We worked hard to get that animation to work, by the way. Okay. So that's our study area, right on the border between Switzerland and Italy. We'll be flying into here about 100 kilometers away to the northwest is the village of Zermatt, best known perhaps because it's sort of a staging area for those people that want to climb the Matterhorn. So that's our study area. This is just a view, obviously from a helicopter, of the village of Zermatt. This is a picture that I took a number of years ago, so showing this typical U-shaped glacial valley, and then within it is the village from which we'll be staging our visit to the glacier. This is just a sort of postcard view of the village of Zermatt. It's not very big. In fact, it's so cramped and small that no gas-powered vehicles are allowed. The only vehicles that are allowed that basically are taxis that are run on electricity. So it's a very environmentally friendly place. The main pollution is actually the goats that they lead through the streets, and they do what goats do.
So last time we had one of our group who drove his car up there and was driving around in the village, and I don't know how he did it or where he found the road, obviously not with permission.
He just acted natural, huh? And
Yes.
like this, I meant to do this. Well, the Swiss are very hierarchical, very Germanic. I think if you act like you know what you're doing, you probably get away with anything for a while. But I wouldn't want to try that. But it's a very fun place to visit. This is a view of the Matterhorn. We were actually there August 2015 on the sesquicentennial of the first ascent to the Matterhorn, and this is a cell phone picture that I took that were actually lighting up the ascent path to the Matterhorn. So that doesn't look like much, but that's actually what you could see going up the side of the Matterhorn.
So those lights were right along that trail, so to speak.
Right along here, I believe, yes.
Yeah, I think it went all the way to the top, didn't they?
Yeah, I assume so, yeah. We've done a lot of camping out here out on the glacier. It's amazing because the Matterhorn looks like a fairly imposing sort of thing to climb, at least from my point of view. I don't even like to climb stairs much. But it's amazing. After dark, the whole place it's lit up, not like that, but there's people camping on various levels. There's perhaps more people camping on the Matterhorn than there were actually on the glacier itself. Well, there's just another view of the Matterhorn. If you have jet lag, you end up taking lots of pictures at all hours of the night and day of the Matterhorn when you first get there. So this is a couple of pictures that I took when I first got there. So this is what you'll be seeing outside your hotel, the Tannenhof. So this is a picture taken from helicopter as we're approaching the glacier. So you're able to see this along the valley wall. Getting out onto the glacier, probably not going to be able to do that because the glacier is pulled away from the valley wall, and you'll probably need more than an ice axe now to get out. The last time I was out there, we had to use a series of ladders and ropes and dumb luck in order to get out there. Now it's probably pretty difficult unless you're riding on a helicopter. And this hat costs probably, I don't know how much money we probably gave to Air Zermatt. Well, it's probably added up to about, you might know, $25,000 or something. This is a very expensive hat. Okay. So this is a movie of this is actually the very first time we went out onto the glacier. It's even got sound. So you'll actually be going here, standing and looking over this. So this is the glacier that we've been studying, this one right here. So that's that. That was Summer Rupert yelling in the background. Okay. So this is a photograph that Adam McKean took, one of the first students to go out there with us. He now works for the Utah Geological Survey doing mapping. It's a great panoramic view. There's the Matterhorn here. The different glaciers that you can see. The ones that we've been studying is this one here, Zwillings, which means, I believe, twins in German. Grins means boundary or border in German. These are the two glaciers that we've been studying, all part of what's called the Gorner Glacier System. Okay, so this is a picture that you'll be able to see. If you're standing right here, that's where this picture came from. So what you'll be doing is coming from Zermatt up a funicular train. You'll get to this point right here, Gornergrat, meaning ridge, and then you'll be able to look out, and this is what you'll be able to see. And again, our study area is right here. One of the first things we did is to collect a radar profile, a ground-penetrating radar profile, microwave energy, so it's about 200 megahertz. That means anything to you for the antenna, and then just note the scale of what we're looking at here. This represents the medial moraine, and that's this feature here. You'll be able to see that. That's where we made camp. So a Google Earth image caught just at the right time to show these ogives very nicely. So this is Zwillings Glacier right here, glacier just German for glacier. And this is what we're trying to understand is what do these ribbed features actually mean? Can they be interpreted in terms of the temperature structure? In other words, are they seasonal features that are related to the distribution of water and thus temperature within the ice? That's
You can't ask questions or make snide remarks.
Oh, yeah.
So feel free to.
Yeah, I'm doing the talking head thing, but this is supposed to be a kind of discussion. So if you don't say anything, I'll just keep going. Okay. So here, okay, good. Customer, finally.
Yeah. So those ogives, can they also form, where would they be forming more or less parallel to transverse crevasses or cracks in the glacier, or?
Yeah, so the question is, how are they related to crevasses? So they're not really crevasses, they're very subtle sort of topographic features. The crevasses are sort of perpendicular to them, although they have quite a complex shape. I don't know if I have any pictures of crevasses, but you can, kind of hard to see from this picture. But yeah, they're basically transverse, vaguely transverse to the crevasses themselves. They are related to the crevasses in a way that I'll explain here in a little bit, but they're not the same as crevasses. Okay, this picture might actually help. So this is, again, a helicopter view showing the layout of our radar profiles, just so you can see what we've been doing. Again, this is something that's been done with students. The students have very much been involved and hopefully will be involved in this. So we did a number of radar profiles. These are hard to do because you're pulling an antenna across very rugged terrain, not just antenna, but other equipment as well. So it's a pretty tough thing to do. Unfortunately, there's people out there a lot stronger than me to help out. The ogives, again, these features, these ribbed features here, kind of hard to see any crevasses, but you can start to see up here where snow is accumulated. These are probably crevasses up here. Okay, these are actually transverse crevasses, but you also have those that are longitudinal as well. A good example is crevasses over here, for example. These are all crevasses.
What time of year was this picture taken? Maybe May or something like that?
This one would have been in July. May is probably covered with snow. I have a May photograph as well. May, you're going to likely be covered with snow. Very dangerous to be out there in May because you can't see anything because you might step in a crevasse or molon or other feature that just has a little thin ice bridge over it. And it's very deceptive because if you're on skis, that may be fine because the stress is much less on a ski than on your boots, particularly if you're carrying 50 pounds of equipment. So we prefer to work during the July and August months, but have been out there in May. So this is just a view from the glacier surface. This is our equipment being loaded. That goes with the hat, right? So that little route probably cost us like $5,000 right there. Okay. This is a view taken from the helicopter of me leading my colleagues on the surface as I was departing. We just went in stages So that's just a view of the glacier surface. Here's another view. This is Scott Ritter, one of our colleagues in the department. This is Summer Roofer taking a picture of me, taking a picture of her. They're just packing up their equipment on what's basically an ice desert. This was actually taken in May. So May, everything's covered up. It's not the best time to work out there. You can see these poles that we used to actually determine if we're actually walking over something that's very thin. I have a picture of this as well. This is just a picture of BYU students assembling the radar equipment. This is fairly high up on the ice surface. This is me showing my better side. And then this is a view going up towards that icefall zone that you couldn't see in that previous picture, but this is actually going up to the icefall zone. One of the things we have to do is use these poles to have someone go. Notice how we're all harnessed in. So if one person goes, maybe they'll keep the other one from falling in. Use the poles to determine how, if there's any thin snow that's bridging over a void that we don't want to walk into. So its progress is very, very slow. So that's in May. So we probably won't see that much snow when we go out, I'm hoping. That's a helicopter view of the icefall zone. That picture I just showed you was actually down here. That's about as far up the glacier as we dared go. But see this blue? This is a bit of water that's collected in one of these crevasses, and this is actually the important part of our story, is that what we'll find is that the introduction of water within crevasses in the icefall zone gets sort of frozen in, so to speak. That latent heat that's associated with the liquid water is retained throughout the year and then is trapped and produces a temperature distribution within the ice. But that's maybe jumping ahead a little bit too much. So, wave ogives. This is just a picture that I took from a helicopter, applied a little bit of shading, and I think you can see the wave pattern is accentuated by it's about a meter of snow that's covering the ice surface. And these trails, these are our radar profiles, so we actually know where we actually went. But these are those ogival features. The icefall zone is way up here. Okay. So one ogive would represent one wavelength, just like you think of any type of wave. So that's one ogive. Again, we think these are seasonal features that are related to the introduction of water into the ice during the summer months. It's frozen in during the winter months, and then is retained as a temperature distribution that we can later detect with the radar. So speaking of radar, this is just a layout of our radar profiles. So north is to Switzerland is here, Italy is just down here to the south. Icefall zone is right here towards the bottom of the slide. The red represents the profiles that we collected. And then we also had a 3D area, the first time anyone's ever done 3D over a glacier, 3D waveform data over a glacier to study ogives. The only time this has ever been done. Quite tedious to do, but we were able to do it.
By the way, you'll be taking gondolas up to the Italian border and walking from Switzerland over to Italy and looking out, is that right? I think you've been up there, but I haven't.
Oh, I've been up there, yeah.
I haven't been on the gondola yet.
It's amazing.
So you actually be able to see this. It was always kind of odd because we felt like, well, we're really remote. This is hard to get here. It's hard. Walking around is extremely difficult. It's not high altitude, but it's high enough that you're a little bit unused to it. And yet we had perfect cell phone coverage. There's hotels, probably 5-star hotels, just above us on the ridge that people can take a train to. And they have these gondolas that are going around. So we're down here roughing it, and all these people sort of watching us. And so you had to really concentrate to feel like you're someplace remote. It was tough.
You can see your field area from going up the gondola. Dave was pointing out, that's where they're working.
Yeah, we were like looking up on the ridge and they were looking down at us. It's like...
Question.
Yes, please.
Oh, so Adam McKean told me that there's a story about like when you were hauling all the supplies out and like the sewage bags that broke on somebody, right?
Yes, but I'd rather not talk about that.
Okay, I wondered if that was the story you want to share or not. So.
Maybe later.
Okay.
I don't have any props for that, okay?
Oh, okay.
Chris, do you know what the elevation is at the top of the gondola? Isn't it like 12 or 13,000 feet?
I think it's 12, I think.
Yeah.
Yeah, it's quite a ways.
You'd
You'll
notice
feel
it.
it.
Yeah, probably, yeah.
But it's still worth it, even if you get a little, and even if you're afraid of heights, it's still worth it, because I am pretty afraid of heights, but it was great.
The elevation along the train is about 3,000 meters, a little over 3,000 meters.
And the top of the Matterhorn's over 15,000 feet, so it's up there. This is just to the saddle, so to speak.
So I'll show you one of our radar profiles. It's this one here in the middle. And I get to the meat of what we're doing here. So this is a profile, like a road cut or cross section, showing radar reflections, but showing it as scattering. Okay, so here's, just for scale, here's 200 meters for scale. This is going down the glacier. This is up the glacier to the south towards Italy. So Italy back towards the village of Zermatt here. This is just showing a inset map. And then vertical scale here, here's 50 meters. Okay, so it's vertically exaggerated by some. And then the glacier surface is here. So this is produced by having an antenna that records the radar waves echoing, just kind of like seismic data, except it's much higher frequency. And what you can see is this sort of sinusoidal pattern. If everybody can see that. It's extremely regular. It's actually even quite predictable as a sinusoid. If you wanted to represent that mathematically, it'd be a combination of a sine function and e to the x. It would look just like that, a decay curve, so to speak. So that's what we're actually seeing with the radar. The icefall zone is up through here, and I've chosen the color scheme so that red represents high scattering, okay, so high reflectivity, and blue represents transparent. In other words, we're not getting any scattering through that. Now, I did that on purpose because our hypothesis is that what is scattering the radar energy? Well, you got two choices, right? This is kind of a dream for a geophysicist because you only have one substance to worry about. Geologists, you go mapping, well, how many different types of rocks and minerals are there? Lots. Well, here you have one mineral. You have H2O. That's all you got, nothing else, okay? You have two states of it, at least, solid and liquid, right? So what's causing the scattering? Well, it's the liquid water, is our hypothesis. And why is it liquid? Because it's a little bit warmer. A lot of studies have shown as you drill through the ice, the temperature goes up. And so that's called a polythermal glacier, more than one temperature distribution. So basically seeing a fossil, so to speak, temperature distribution preserved within the ice that's developed over several tens of years. So that's our hypothesis. First time anybody's actually ever seen anything exactly like this. One other case, but that glacier is gone. But this is the best study that's ever been done for this type of feature. This is just a close-up. We did cross lines, so if you're a geophysicist doing seismic data collection, you always have dip lines and strike lines, right? Geologists think in terms of dip line and a strike line. This represents a dip line that's down the glacier, and this is transverse or across the glacier line. So you see a clear differentiation. These represent our scattering. And notice how they're spaced. They have a definite space to them. As you go down the glacier, they get closer together. Up the glacier, they get further apart. If you look at it in cross-section, in the perpendicular view, you see a lot of planar features like these. We suspect these represent zones of perhaps shearing along which water has collected. Again, you don't have any other way to explain it. It's not like you have different rock types. There's not like sheets of metal in there. You basically have the choices of liquid water or solid water. So we think that represents liquid water that is scattering the energy in a planar sense and in a more diffuse sense.
So when the lake would form the junction of the two glaciers every year and then drain catastrophically, would that change the scattering on
I don't
those
think
areas?
that's related. That's just another location.
Okay.
But in that sense, though, you have smaller lakes, or lakelets, I don't think that's a word, but that would allow the ice to incorporate water that then is sort of frozen in. Because once you put water deep into the ice during the summer months, and then it's locked in, it doesn't assume some sort of steady state system, all right? It doesn't all become homogenized to one temperature. That latent heat is still there as liquid water. It's a property that we had to struggle with at first, but once that water goes in, it stays warm. Just enough to keep it in a liquid state. This is a 3D volume that Bill Keach produced using software that's meant to be used for seismic exploration. But we've actually used it to look at the scattering pattern in 3D, and this is just a little movie of that. So this represents your ogive features here, your scattering, just as I showed you in that last slide, and then the planar features. can also be seen cutting through that in a transverse sense. So again, this is the first time anybody's actually been able to see this. We use special processing in order to sort of see through the ice. So we're actually not seeing the ice, that's black, we're just seeing that which is scattering the light. So again, the first time anybody has actually ever done this. This was published in the paper that I think you all received as an email link. Okay, so it's not going to be a hit on YouTube, I don't think, but again, it shows in a very three-dimensional dynamic way what the scattering looks like. So we're just coming around and looking at the other way. Okay, so that's probably enough for that. So what's actually causing the reflectivity? So here's just one profile through one of these ogive features, and this represents the apices of a diffraction or a scattering point. And we can use some mathematics, which I won't go into, so you kind of get an idea how big these things are, because that should be your question. Well, how big are these things? And what we came up with is maybe somewhere around 5 meters. So I can't stretch my arms quite that big, but you get the idea, around 15 feet. That you have pockets maybe of water that's actually causing this scattering of light. What we also did is like, well, okay, how is the scattering related to the surface of the ice? Okay, so this is a diagram that shows in red the radar scattering, and then the topography drapes the scattering pattern over the actual ice topography in a place where we did the 3D, so we have very detailed coverage, not quite LiDAR, but almost LiDAR-like coverage. And I think I have a little movie of that, which I'll just show part of. But the red represents the scattering, the periodic scattering, and what you can see is that it has some relationship to the wavy character of the ice. It's not a perfect association because it's deformed at this point, but we intuited that, well, there must be some relationship to the ogive patterns. The ogive pattern is what is represented by the waves on the surface of the ice. So if there's a relationship that we can show between the scattering, which is shown in red, and the topography, which is represented on the diagram, well, then we can start to make some explanation for what the scattering is actually being caused by. So one way to do that is just to do some statistics, which I won't get into, is quite detailed. But if we look at, say, the gradient of the ice topography, we compute the gradient, the first derivative, also the second derivative of the surface, then we get these patterns such as you see here. And you notice they're kind of they have a certain periodicity and then decaying as you go down the glacier. If we compare that with the scattering pattern in the radar profile, which is shown here statistically, and then also looking at the gradient, then we see a correlation between the scattering within the glacial ice and the topographic expression, which is quite subtle. It's quite subtle, so you have to do some mathematics to actually see it, but there's a relationship between the two, which suggests that somehow the ogives are affecting how water is getting into the ice to produce that scattering.